we're going to move to the next segment. And really what we're going to do is extend our chemistry knowledge a little bit. And we're going to see what happens to atoms when they react. And so the atom was put together with three components, three particles: electrons, protons, and neutrons. The number of protons in an atom defines what element it is and defines how it reacts. The neutrons actually can be variable. I can have a couple more, or I can have a couple less, and they weigh different things, but it doesn't change very much their reactivity. In general, they react all the same. The electrons are not in the nucleus. The other two are in that little tiny ball in the center where all the mass is. The electrons are in that big volume just floating around, moving around. Now, if you study chemistry, they are actually really defined spaces, but for our knowledge, they're just in that volume. Okay? In terms of the reaction, what actually occurs in a chemical reaction is interactions with electrons. And that is simply it. In radioactivity, we can actually change the nucleus. So if things happen in the nucleus, it's radioactive. And if it's just chemistry reactions, it's in the electrons. There are two places within the atom that we manipulate. And for most things, we actually can control and do chemistry in the lab. I don't want to do nuclear processes in the lab with you guys. And so we don't bring that in. We're actually not authorized to have radioactivity anymore. But when we had the old building and we moved, it was kind of scary what we found. Way back in the crevices, the kinds of radioactivity. We actually had someone from Oak Ridge National Labs to come up and do measurements to see if we actually had any dangerous radioactive material, but most of what we had decayed. And so I was very pleased because it would have been costly to get rid of it. And so, but we're going to look now and move towards what kind of chemical reactions and try to see what might happen. And so we're going to look at the periodic table and describe why we call it the periodic table. One video to kind of start us off. Okay, so alchemy. It was what they called proto-science. It was before science. And one of the most famous ideas that come with alchemy is people trying to do this. They have a whole bunch of gray, soft, very heavy metal called lead. But they really wanted a whole bunch of really soft, heavy metal that was gold colored. And so what they attempted to do was manipulate or react or do something to the lead to convert it into something that was precious, gold. Now, we now understand that conversion of one element into another element is strictly within the design of the atoms. Some atoms are unstable and they break down, but they break down in very consistent ways, and there is no way lead is going to break down and become gold. There was no way to manipulate that. All right, but they didn't know that, and they attempted to do things. Now, one thing about alchemists was this, is that, and this is one important part about science, is they tried something. They did an experiment, and they recorded what they saw. And by doing lots and lots of experiments and recording what they saw and sharing that, started to build the process of science itself and actually started collecting some information. Unfortunately, some of that process was, as they talked about, not only are they doing an experiment, but they go in and do an incantation or pray to a god to help the process out, because they didn't understand they were basic principles within nature that they were manipulating. They thought something magical might be part of the process. And so we obviously know that it isn't magic, but the systematic look was what led us to what now are modern sciences. Now, alchemy and chemistry actually looked at what we call matter. That means something that takes up space and has mass. Basically anything we can touch, we can grab, we can measure, we can manipulate is matter. Even the air, although we can't see it, we can feel its effects and we can manipulate it, we can trap it and we can compress it. It's stuff, it has weight. The one thing that we don't deal with in terms of chemistry, it is absolutely a non-spiritual, we don't think about the spiritual aspect, which makes it kind of hard to have integration of faith and learning sometimes, because that's not the goal of chemistry. The goal is, how do we describe what is here? But when you think about it, what is here is because of God, so when we see his handiwork, we see God. And in terms of chemistry, what we are really trying to do is find the fundamental patterns of what can happen. And if we then know the patterns of what can happen, we can set up stepwise manipulations of chemicals to make things that are useful, like a drug or like a polymer that might be able to be used for some good purpose. And so the beginnings of chemistry was just doing things and finding out what they did, and then starting to classify the things that we saw that were the same, the things that we saw that were different. Now, a chemical reaction is taking two elements, at least, okay, and combining them together in some way. That is very simply what happens. Now, when the two elements come together, they react at the level of the electrons, and I'll describe a couple ways that the electrons can be manipulated. But what is important is that whatever you start with, okay, have chemical properties. They behave they behave in the world like two things, and then the compound that they make, so elements will combine to make compounds, will have totally different properties than what we started with. An example, sodium. Sodium is a metal, okay, it's shiny, and you can actually take a knife and cut it. It is very soft, almost like soft butter. And you can manipulate it, and you can slice it off, and you can have that little sliver of sodium metal, okay? And you see it's shiny just like any other metal that you would think. Now, if I took that sodium metal, the element, and I put it in my fingers and I plopped it in my mouth, okay, what would happen? Would I have a good day that day? No. The sodium metal would react with water in my mouth, and an explosion would happen, and I would die. Okay? And this is not a good day for the professor. All right. So sodium metal is kind of dangerous. All right. Here is a gas. It's in a bottle, and the gas is chlorine. The element is number 17 up there, chlorine gas, little greenish. And I could take a bottle of it and put a hose on it and put a mask and put it up to my face and turn on the gas, and you see the green gas come. And if I took a big breath of chlorine gas, what would happen to me? I would die pretty quickly, because chlorine gas is poisonous. All right, so sodium metal, if I take that in my mouth, I die, and chlorine gas, if I breathe that in, I die. All right. If I take the sodium metal and I take the chlorine gas and I mix them together and add just a little bit of heat to start the reaction, a very bright reaction will occur. It will look like it's burning. And it will burn and burn and burn. It looks like burning. And it will create a white smoke, and that white smoke will go to the surface of the glass, and it will cake on the edges. And when the sodium and the chlorine react completely, I could open up the container, I could take my finger, take that white powder, and put it in my mouth, and you know what would happen to me? I would not die immediately, because what I've just made is sodium chloride table salt, and I don't die immediately, but my blood pressure goes up and I might die later of hypertension. Okay? But the sodium chloride compound has totally different properties than the two elements from which it came from. Now, sodium chloride gives us flavor. For a long time, sodium chloride was used to preserve meats before refrigeration. Sodium chloride, the salt, was actually so valuable at times in terms of a preservative that even the Roman soldiers were paid in salt, an amount of salt, rather than in coins or money. And so salt is very important. But those two elements by themselves, not so good for me. Put them together, I create something brand new that has absolutely different interactions with the world. And so chemistry is important because it changes what kind of interaction our elements can have with the world. Excuse me. An example could be zinc and sulfur. Zinc is a metal, sulfur is a powdery yellow substance, and each of these particular entities have certain characteristics. This melts over 400, this melts at about 100. This one is heavy, weighing about 7.1 grams for every cubic centimeter. This one's rather light, 2 grams for every centimeter. So they're different. This one will dissolve in acids. This one doesn't care about acids, doesn't dissolve. This one doesn't dissolve in this particular solvent, but this one can dissolve. And so they have very different properties. If by chance I took the powdered sulfur and the powdered zinc and I put them into a dish and I just stirred them up in a dish, all right, I'd have a mixture of gray stuff and a mixture of yellow stuff. And nothing would actually happen. I would just mix the two elements together. If I had the patience, I could put it on a microscope with tweezers and I could move all the gray and move all of the yellow and separate them back out, and nothing would have happened. But if I put them in a beaker and I add just a little bit of heat to start the reaction, they will combine together, become a solid chunk, and turn white. And I will make a compound called zinc sulfide, which is brittle. So if I hit it with a hammer, it would shatter like a plate. It doesn't melt. It can go up to 600 degrees, but at that point in time, it may break back into the two elements. Its density is between the two. And this doesn't dissolve in anything that the others were. It has totally different properties than the two things before. And so, by adding two things together and allowing a reaction to occur, I can create something brand new. Now, an element, all right, is one collection of atoms that are all the same in terms of number of protons, number of electrons, and they may have a little bit different neutrons, but that's okay. An element you can find, or you know it's an element if I write it, if you have something written and it has one capital letter. Okay, that's an element. A compound is at least two elements that are written together, okay? And because they're together with no spaces, that meant they are combined. And a compound can be identified because it is something that has more than one capital letter in it. And so if I write the symbols, okay, sodium plus chlorine, they are by themselves, okay? I have a plus between them, so they're not connected. And then if I write sodium chloride, do you see there is no space between them? That means they're together, they're combined. The compound is the second one, and the two elements are the first one. Now, compounds and elements can be found all over the earth. And all matter is available to us. But there are two kinds of matter that you can have. You can have something that is pure, and then you can have something that is a mixture. Now, in terms of purity, yes, there are pure things on earth, but really it's very hard to get anything absolutely pure. Even when I go to the chemical company and I order a chemical and it's got a bottle and it's got a name on it, usually there's a purity, and if I can buy something that has 99.9%, that's pretty good. You can even buy things that are 99.999% in terms of purity, but sometimes the best I can get is that chemical and it says 85%. That means there's 15% of other stuff in there that I'm not exactly sure what it is. And so getting something absolutely pure is kind of hard. We could find a pure element that is only one kind of atom. That's cool. Or we could have a pure compound, meaning that two atoms have come together, they are connected, and then when I collect everything, it's just that compound. All right, like water. I could have pure water. Now, does anybody drink pure water here? Where would you get pure water? In a bottle? Actually, pure water is very hard to achieve. If you get it out of the tap, that's not pure, right? Sometimes you get sulfur water. In the tap water, what do they put in tap water to protect you? Fluoride, chlorine to break down any bacteria to make it safe. So even the tap water that we get looks pure, but there's stuff in it. All right. If you get a bottled water, you got to watch your bottled water. Sometimes it says purified. Okay. Purified can be as little as running it through the tap and running it through a piece of filter paper, which doesn't take out much of anything. Okay. You can get distilled water, in which you boil water over and you collect the steam. That is more purified, but things can go over with the steam too. All right. Most of the time you buy what's called spring water, and that spring water is just water out of a tap. Okay. It came from a spring, and they can sell it to you. All right. We actually try to use pure water in the laboratory. We have to take the water, we have to distill it, and then we have to take it through these big old filters. You may have filters at home. We have like filters that are this big, this long, and 3 of them to try to extract everything out of the water. And we know if we have pure water by measuring, does it conduct electricity? Okay? If you stood in a puddle and a lightning bolt hit, what happens to you? You die. You're electrocuted. Now, it's not because of the water. It's because of the stuff in the water. That's what carries the electricity. Water itself carries no electricity, but only in a pure form. So when we get water and it doesn't conduct electricity, we know we've got it pure, but it takes a long time to get there. So we can find pure elements and we can find pure compounds. It's just, it takes a lot of work to get them. Most everything in the earth is a mixture. There are 2 kinds of mixtures. Something called homogeneous and something that is called heterogeneous. Homogeneous mixtures have a special name called solutions, and a heterogeneous mixture doesn't have anything special about it. What's the difference? Okay. A homogeneous mixture is that if you take a look at it, can you see the two things mixed together? Okay? And that's going to make the difference. If you can't see the two things mixed together, it's homogeneous. If you can see the two things mixed together, it's heterogeneous. Example. A glass of water in which I poured just a little bit of salt and stirred it up. If I handed it to you and you looked at it, it looks perfectly crystal clear. Okay? But if you taste it, what happens? It tastes gross. Okay? When you look at it, you can't see the salt in it. That is a homogeneous mixture or a solution. All right? If I put sand and stirred it up in water and I handed it to you, you're not going to get tricked, right? Because you're going to see the material in there. That's a heterogeneous mixture. Now, solutions might make you think that it is just liquids. Okay? The air in the room consists of all gases in the atmosphere. There are two big ones, nitrogen and oxygen. Which one's important to us? Which one? Oxygen. Carries that oxygen, allows our bodies to burn our fuel and give us energy. So we want oxygen in there. But this particular air that we are breathing is a mixture, and it's homogeneous because we can't see the oxygen and the nitrogen. Now, I might make an argument if you're in LA and you look at the air, that might be a heterogeneous mixture because you might see the smog in it. Okay? So a solution, you can have a solution of gases. You can have a solution of liquids. Ah, my ring. My ring is gold. Okay, my ring is 24 karat gold. Is that pure gold? 24 karat. No, it is not. It's the highest carat value that you can get in jewelry. All right? Why do we not make a pure gold ring? Yeah, it's too malleable. You'd actually squeeze it and it would just bend. Okay? What they do is they put gold and other metals together and mix them up. Could I see all the other metals in this ring? This is a solution of solids. Okay? And so I can have a solution of solids or liquids or gases. And so we can have lots and lots of different mixtures. Most of the time, if we do have something mixed up, it is heterogeneous. We can see it. Okay? But every so often there can be a mixture in which we don't see the different pieces of it. Most things are mixtures.